Right, so this is the introduction to differentiating logarithms. A few different topics we're going to look at here. We're going to look at how we differentiate a logarithm to base e, using log laws to simplify differentiation, differentiating a logarithm with a base other than e, and then some application problems as well to round it out. But in this video, we're just going to look at the proof for how we differentiate a log to base e, and then a few worked examples as well to go with that. So, firstly, if we're differentiating a log to base e, what we're going to start with is we're going to start with our basic. I'm just going to call it ln x, same as log to base e. Now, where this proof comes from for the derivative, what we're going to do is we're going to rewrite this, and we're going to rewrite this in index form. So we're going to rewrite this as x equals, our base is e, so e to the power of y. Now, why we do that is because we can actually differentiate that. It won't be dy on dx though, it will be dx on dy, and if we differentiate that, we end up with itself. E to the y just differentiates to e to the y with respect to y. Now, just a reminder, this is what we're being tasked to differentiate. Now, given that fact, we want to find dy on a expression for dy on dx. So therefore, we're going to take the reciprocal of this, dy on dx equals, and therefore, on this right-hand side, the reciprocal of that will be 1 on e to the power of y. Now, from above, we actually already have an expression for e to the y. That is, we defined that earlier. E to the y is actually equal to x. So therefore, dy on dx is equal to 1 on x. So our actual differentiation here, when we differentiate a log to base e, so ln x, you end up with 1 over x. Right, which is very useful. So you might notice why that's going to be useful, because when we come to integration later on and we want to integrate 1 on x, we know now that that will actually equal ln x, and we've had difficulties integrating that in the past because when we were to bring that up, we get to power minus 1, and then we couldn't raise that power and divide by it. So we have actually encountered this expression on a few occasions, and in some of the previous work that we've done, so it won't be too unfamiliar to it, but that's the proof of how we differentiate a log to base e of x. Now, what happens when we want to differentiate a log to base e of an expression other than x? So, for example, what that might look like is that might be that we want to differentiate log to base e of 3x plus 1, for example. Well, how do we go about doing that? Well, what we're going to do here is we're going to take a similar approach. I'm going to write down y equals ln of f of x. And what we're going to do here is we're going to let u equal f of x. Therefore, u dash, when we differentiate that, equals, so rather than using u dash, that's something that we normally associate with the product rule, we'll call this du on dx equals f dash of x. Then if u equals f of x, y equals ln u, and therefore dy on du is equal to 1 on u, and u we've already identified as 1 on f of x, so therefore that equals 1 on f of x. So if we've got an expression now for dy on dx, and we have an expression for dy on du, then just a reminder, using the chain rule, dy on dx is equal to dy on du times by du on dx. Dy on du is 1 on f of x, and du on dx is f dash of x. So when we multiply these together, we get f dash of x on f of x. So therefore, if you differentiate log to base e of f of x, that differentiates to f dash of x on f of x. And what we're going to do now is we're going to look at a few worked examples of this and what this actually looks like. So starting off with our worked example here, you can see that it's not just a single x, it's not log e of x, it's log e of x minus 3. So just a reminder what this looks like. If you differentiate log to base e of f of x, what we end up with from here is we end up with f dash of x on f of x. So it's important here that we identify, well, what is f of x in this instance? Well, f of x is equal to x minus 3 and f dash of x. Therefore, if we differentiate x minus 3, we end up with 1. So therefore, dy on dx is equal to f dash of x. So f dash of x is 1 over f of x, which is x minus 3. And that would be the derivative. Right, moving on. Similar question, but we've got some negatives involved here. Not that that changes things. So we'll let f of x equals negative 3x minus 6. F dash of x, therefore, equals negative 3. And then if we go into our derivative, dy on dx is equal to f dash of x, so minus 3, over f of x, which is minus 3x minus 6. Now, this we can actually simplify. Let's move that up there. You might notice that each of those terms in this expression all divide through by negative 3. Negative 3 divided by negative 3 is 1. Negative 3 divided by negative 3 is 1x. And negative 3 divided by negative 3 is 2. So we get 1 on x plus 2. All right. Moving on from here, we end up with, we've got, our next example is y equals 3 lots of log e 5x. Well, this doesn't affect the f of x. So the f of x is still the function within the log. So f of x, sorry, the term within the log is 5. So f of x is 5x. F dash of x is just 5. So therefore, dy on dx is equal to 3 lots of f dash of x, so 5, over f of x, which is 5x, which is equal to, well, firstly the 5's cancel with each other, and we're left with 3 over x. Okay. Similar example here. Again, the 6 does not affect the function. F of x equals 2x plus 9. Therefore, f dash of x equals 2. Therefore, we end up with dy on dx equals 6 lots of, differential of 2x plus 9 is 2. And f of x equals 2x plus 9. And if we simplify this, we get 12 on 2x plus 9 is our derivative. We can't simplify that. There's no common factors between those 3 terms. Looking at our next example, what we've got here is we've got a succession of terms. So let's let y equal that. And so when we're differentiating this expression here, we differentiate the first term, so we get 3x squared. The next term, we differentiate that to minus 3. The next term is a constant, so that's removed. And then we differentiate the log. Well, the differential of the f of x part is 5 over 5x minus 7. Done. So we just differentiate each of those terms individually. Now, with this question here, we're going to look at this in 2 different parts. We're going to look at this in the part of using some log laws, but also just using the normal method that we've looked at already. So method 1. What we've got here is we've got, well, f of x equals x to the minus 2. So therefore, f dash of x is equal to negative 2 x to the minus 3. So therefore, and there is going to be some simplification with this, therefore dy on dx is equal to f dash of x, so minus 2x lots of minus 3 on x to the minus 2. Now, when you're dividing, you subtract the powers, so minus 3 negative, or minus 3 subtract minus 2, means it becomes minus 3 plus 2, which is minus 1. So we end up with minus 2x to minus 1, which is negative 2 on x. Now, we're going to use method 2. There's also another approach we could take here, and that is we can use a log law to simplify. So first of all, if we simplify What happens is, what we do is we can write this as y equals, now because this is a power, remember using that log law, we can bring that power down to the front. Y equals -2 log of x. Now, when we differentiate that, log of x, remember, it just differentiates to 1 on x. So this becomes -2 times by 1 on x, which is -2 on x. Notice that both of our answers are exactly the same. Okay. I'm just going to stop that there, and then we'll look at the product and the quotient rule separately.